To find the coefficient of friction, the first part is to deal with the initial impulse, which is caused by the force applied by the skater. Forces acting on the skater in this initial part are the force applied that will cause the skater to move at an impulse velocity, the normal force, as well as the gravitational force. The impulse velocity is equal to the initial velocity when the skater starts moving.
As the skater starts moving, the only horizontal force acting on the skater is friction. Other forces include the normal force and the gravitational force. Since the final velocity is 0, the skater is decelerating to a stop.
Impulse is equal to the force applied to an object over a period of time. That is also equal to the change in momentum times, which is equal to the mass total times the change in velocity. Since these equations are both equal to impulse, we can set them equal to each other. Since the skater started from rest, velocity naught is equal to 0.
Using the impulse velocity as the initial velocity, we can solve for the average velocity since the final velocity is 0. Knowing the average velocity and the time in seconds, we can solve for the distance the skater has traveled. Using this kinematic equation that involves displacement of an object, we can solve for the acceleration. The acceleration should be negative because the skater is decelerating.
Using Newton's second law of motion, the net force is equal to mass times the acceleration of what we found from the previous equation. Because friction is the only horizontal force acting on the skater, the net force is equal to the frictional force. Since friction is equal to the coefficient of friction times the normal force, we know that the coefficient of friction is equal to the frictional force divided by the normal force. Since the skater was not moving vertically, we know that the normal force is equal to the gravitational force.
Trial 1 refers to Pat being the skater. So for the initial impulse, we measured the force applied using the weight scale, which came to 1099.15 newtons. As seen here, we use this conversion from pounds to newtons. The mass total is 86.2 kilograms. Mass total right here in this equation and right here. As seen here, we use that conversion again from pounds to kilograms. Using a stopwatch, Pat applied the force to the scale for about 0.85 seconds. That's the time right here and right there. Using this information, we solve for the impulse velocity because the initial velocity of the force applied is 0. Thus, the impulse velocity is 10.8 meters per second.
Using the impulse velocity as the initial velocity, and knowing that the final velocity is 0, we found that the average velocity is 5.4 meters per second. We were able to find the distance traveled by multiplying the time of the distance traveled, which is 4.65 seconds, by the average velocity of 5.4 meters per second, making the distance traveled 25.1 meters. Using kinematics, we know the initial velocity, the distance traveled, and that the final velocity is 0, we can find acceleration, which ends up being negative 2.32 meters per second squared.
Using the same process for finding Pat's calculations, we solved for Heather's calculations with her applied force being 903.35 newtons, her mass total being 59.02 kilograms, and the time for the applied force being 0.60 seconds. Using this data, we found that her impulse velocity is 9.18 meters per second.
Using the same kinematic equations, Heather's average velocity was 4.59 meters per second. Knowing her travel time is 6.9 seconds, we solve for the distance, which is 31.7 meters. Using this information, we solve for acceleration, which is a negative 1.33 meters per second.
Going back to trial 1 and referring to Newton's second law of motion, we found Pat's frictional force using his total mass of 86.26 kilograms and multiplying it by his acceleration of negative 2.33 meters per second squared, resulting in negative 201 newtons. Because the frictional force is equal to the coefficient of friction times the normal force, we had to solve for the normal force, which is equal to the gravitational force, which is 845 newtons. Thus, to solve for the coefficient of friction, we had to divide the magnitude of the frictional force by the normal force, not the direction, which gives us a coefficient of friction of 0.238.
Using the same ideas, we found that Heather's frictional force is a negative 78.5 newtons, and her normal force is 578 newtons. Thus, her coefficient of friction is 0.136 when you divide those numbers.